Okay, hello, and today I'm going to give you some notes on beat frequencies and scales. And before we do that, let's look at some results from last time when you did well, let's start with some definitions actually. I gave you that worksheet on resonating frequencies, and I didn't really tell you what I meant by harmonic and fundamental frequency, so I'm going to tell you that just to define it. Um, when we talk about ways that a wave can sit in a pipe in one of its natural modes of vibration, there are only certain ways a wave can sit in there, and those are called the harmonics. So for an open pipe, these are pictures of an open pipe. This is the simplest way you could get a wave to sit in there with antinode, node, antinode. And this is talking about where the pressure is changing a lot, where the pressure is not changing at all, and where the pressure is changing a lot again. That's the simplest way, and that's called the first harmonic. This is the second harmonic. This is the third harmonic. That's just that each of these is the next simplest way that you could get air to sit in that pipe with an oscillation. The simplest way, the first harmonic, is also called the fundamental frequency. Actually, speaking of open pipes, let me just show you an example of a whirly, which is an open pipe. Is open on. Okay, this pipe is open on both ends, so this is an open pipe. And I found this volunteer to make it go faster and faster and faster, and you get higher frequencies when you make it go faster. Okay, so the whirly is an example of an open pipe, and that lots of different instruments are open pipes. A flute is an open pipe. Even a trumpet, I believe, is technically an open pipe. Clarinet is a closed pipe. Where the end where your mouth is with the reed is a node. So these are closed pipes, and the way a wave sits in there at the fundamental frequency is actually there's only a quarter of a wavelength here. I hope you can see that. This is if this is one lemon, this is just a half of a lemon. So you need two full lemons to make a full wavelength. So that's a quarter wavelength in that closed pipe. That's a fundamental frequency, or the first harmonic. And this one is the next harmonic, but it's actually not the second. It's the third harmonic, and this is the fifth harmonic. And you saw that mathematically when you derived the formulas. So the formulas you found, let's see. Okay, so yeah, first, second, third for open pipes, first, third, fifth for closed pipes. And that comes from the fact that the third harmonic is 3 times the first harmonic frequency. That this frequency is 3 times this frequency. So if this is 100 hertz, this is 300 hertz, this is 500 hertz, etc. If this is 100 hertz, this is 200 hertz, 300 hertz, etc. So it multiplies that way. Here's a summary of the formulas that you found on that worksheet. This is the formula for closed pipes, and this is the formula for open pipes, and it's also the formula for strings. And that's for the nth harmonic. So for the first harmonic, or the fundamental, it's just V over 2L. For the second harmonic, for open pipe, it's going to be 2V over 2L, or just V over L, etc. And then for closed pipes, you can't use n equals 2. You can't use even numbers there. It's all odd numbers, 1, 3, 5, 7, etc. There are no even harmonics in closed pipe instruments. Okay, so that's a summary of what we did. And now let's talk about this idea of beat frequency. So here's a definition for you. Beat frequency is another frequency that you hear when you play 2 notes. So actually it's not a second, it's a third frequency, because you play 2, then you hear 1 more. And we call that the beat frequency. And sometimes if it's a low frequency that's not a pitch that you could hear, like out of your hearing range, of, lower than 20 hertz or so, then you might just hear wow, 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 like at a 1 hertz frequency, or 2, wow, 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 like 2 hertz frequency. I'll give you an example with some notes in a minute. But if it's a frequency you can hear, you'll actually hear a third pitch. Okay. And by the way, the beat frequency is the difference of the 2 frequencies. Okay, let me show you some examples. Okay, I'm going to start by playing a 200 hertz pitch frequency. Okay, there's 200 hertz, and now I'm going to play on another tone generator. I'm going to play 201 hertz, and you're going to hear a beat frequency at 1 hertz. Ready? Go. Okay, let's move it up to 202. Now the beat frequency is 2 hertz, 2 per second. 3 hertz. Beat frequency 4 hertz. 5. Now if we get the beat frequency up into the range that we can hear, you know, this is a 70 hertz beat frequency, you're going to hear a third pitch. Besides the 200 and the 288, you're going to hear an 88. Do you hear that? Are you starting to hear that low note coming in? There's a note down there. Okay. Okay, so now watch this. I'm going to play a middle C, which is 262 hertz. And then I'm going to add on top of it the G above it, it's a nice sounding chord. The C and the G together sounds good. Here's the G above it. It's the letter G note, but it's 392 hertz. But did you notice when I added that you heard another note down low? I'll turn this first one off so that you can just hear what the 392 is supposed to sound like. It's a high note. It's a high note. So let's try it again, starting with this 262. Add this high note, and you also hear that low note. The note you're hearing is this note, right? Isn't that the low note you're hearing? That's 131. Why? Because 392 minus 262 gives you 131. That's the beat frequency, but it's also another note. And it matters. That note matters because 131 is half of 262, which means they're an octave apart, which means they sound good together. So when you play a C and a G, you hear another low C. It's half the frequency of 262, so it's an octave below it. And that's why C and G sound good together, because the beat frequency sounds good with one of them. All right, so basically, if two tones are harmonics of each other, the beat frequency will sound good. Otherwise, it won't sound good. In other words, if the beat frequency sounds good, two notes sound good together. That's another way to say it. And that's why some of these really simple ratios of frequencies sound good. An octave is a 2-to-1 ratio. A fifth is a 3-to-2 ratio. A fourth is a 4-to-3 ratio. And that's because if you take the beat frequency, you're going to find that it gives you an octave of one of the notes. So it's the beat frequency makes it sound good. By the way, a fifth, if you're wondering what a fifth is, it's like twinkle, twinkle, that's a fifth. A fourth is like Here Comes the Bride, like here comes the bride, that's a fourth. So those are intervals you hear a lot, and there's a reason for that. It's because they sound good. Okay, so from C to G is a fifth, and you can see that it's 1, 2, 3, 4. Wow, 1, 2, 3. Only 4 steps. So why is it a fifth? Well, C to D is 1 step, D to E, E to F, F to G. But that's 4 steps, but 5 notes. So that's why it's called a fifth. But it's a little misleading because there are also half steps in between. C sharp, D, E, D sharp, E, F, and there's no half step between E and F, and then F sharp, G, etc. I'm not singing that in tune, but just trying to give you a sense of these half. If you've played on a piano, played around on a piano, you know what I'm talking about. And if you haven't, you should. So we could build a scale by starting from the beginning of the scale and adding going with perfect intervals. We could start from the first note of the scale and go up a fifth and calculate exactly what G should be, and then go down a fourth and calculate what D should be, and go up another fifth and calculate what A should be, and go down a fourth and calculate E, and do that until we've built an entire scale of notes, and this scale would sound terrible. Let me show you what. For a scale to sound good, the first needs to be an octave below the eighth note of the scale, which is the octave above, right? But 262 times 2 is not 559. In fact, it's 524. So these two notes will be way out of tune with each other, even though all the fifths are correct and all the fourths are correct. You can go on with the online tone generator and try to play 262 and 559 together. They sound terrible. All right, so how do we build a better scale? We need to have 524 at the top, and yet we want the fifths to sound good and we want the fourths to sound good. And the way that we do it is what's called the equally tempered scale. We make every interval about the same, and we divide it. There are actually 12. These are called semitones or half steps from C to C sharp, from C sharp to D. Each of those there are 12 of those from C to the next C. You can try that on a piano. And so we split it up into 12 equal steps, and we calculate how big each step should be. And that looks like this. Every time why are we multiplying by 1.059? Because that is the factor that when you do this 12 times, when you multiply 262 times this factor 12 times, you get 524. Does that make all the fifths and fourths correct? No. But then what a piano tuner does, or anyone who's tuning an instrument, is they tune the fifths a little bit better, especially if you're going to mostly play in C, they'll tune the G to the C pretty well, but it has to work in other keys too. So it's not perfect. The equally tempered scale isn't perfect, but it's better than this one. So the issue with the equally tempered scale is that some intervals will be out of tune from perfect, but at least the octaves will be in tune, and the fifths will, if you tune the fifths a little bit better, then generally things work out, and that's what we're used to. That's what we're used to with pianos. There's no other way around it. If you have an instrument that has to be tuned the same every time, you can't retune it depending on, the song you're playing. So you need to just go with something that's equally tempered and is pretty close. So we're going to be using an equally tempered scale. And this is useful for us because say you know the frequency of your lowest note. For example, say you're designing a musical instrument like you're going to be doing out of straws or little rolled up pieces of paper or whatever you have. We'll do this. We'll figure this out. Let's call them straws. And you're going to be calculating the lengths that you should have for different notes. Well, if you can calculate the length of your lowest note, maybe it's not 262, but whatever it is, if you multiply that frequency by 1.059, now you know what frequency C sharp is, or if that's C. Or if you multiply it by 1.059 2 times, now you've got a D, frequency of D. So this is how you're going to be calculating frequencies, and from the frequencies you'll calculate the lengths of your pipes. Okay, and we'll talk about this next class. We'll have about 15 minutes of everyone together, and I'll talk about this some more, and then you guys will get started working on that lab. Okay, see you then.